Hello, this unit is on the transformer. The transformer has taken over natural language processing. And this year I've expanded the section on the transformer and divided it into two parts. So this is going to be the first part on the transformer. Okay, the transformer was introduced in a paper called Attention is All You Need. We talked about attention last time in machine translation, where it established a correspondence between the input and output sentence words. The transformer can be viewed as attention on steroids, and we're going to go through that in a lot of detail. And as I said, it has essentially replaced recurrent neural networks, RNNs, in natural language processing. And the recent progress on the general language understanding evaluation, BLUE, is largely due to transformer models. Transformer language models, and we'll talk a little bit more about that. The transformer has layers. So you have an input layer and then various layers above the input layer. Each layer has the same shape. It has a time index corresponding to where you are in the text. So you can think of the time index as ranging over a word or a position or a token in the text. Think of it as a word, just for conceptual simplicity. And for each word, we have a vector. And so each layer is assigning a vector to each word in the input. And the vectors are getting more and more sophisticated, hopefully, as we go up the layers. Now that is the same structure that we have in a layered RNN. You have an RNN running over the input words, and then you have an RNN running over the output of the first RNN, and so on, and they get layered. So we had a picture earlier in the units of layered RNNs. The main difference between the transformer and an RNN is that the transformer is computing these layers in parallel over, it's not going sequentially through time, it's going in parallel across all time simultaneously. So in that sense, it's more like a convolutional neural network in the sense that in parallel, in logarithmic time, where the log comes from trees that add large numbers of numbers, so some addition tree in parallel can be run in proportion to its depth, which is logarithmic. But so in basically logarithmic time, you can construct the next layer in parallel, right? So if all the computation can be done in parallel, we're going very fast. And these days, people use really massive parallelism. So it's the parallel runtime that has become more important, especially if you're in industry where you have tons of compute power. Okay, so that is one big advantage. It's not just the attention phenomenon, which is also important, but the other big advantage is that it's faster. Self-attention. This is the fundamental innovation of the transformer. And I want to introduce this in a way that makes the intuition clear. So each position, little t, we want to think of this as pointing at a position or a word in a sentence. So t is range, I'm thinking of that as being time. The words come one at a time, and there's a time, and at that time there's a word. So I'm thinking of t as being a position or a word in the sentence. And so for each position in the sentence, we're going to construct an attention, and we'll review what an attention is. We're going to construct an attention from that position to the other positions in the sentence. So it's called a self-attention, meaning that we've got this one layer that's attending to itself. So unlike in machine translation, where you have an attention that's aligning an input and an output, here we have one layer and the attentions are within that layer. So it's a self-attention. Now, so if I pick a position, a word, and I build an attention from that word is paying, the attention this word is paying to the other words in the sentence, that defines a kind of weighted graph, right? For this word, it's connected to other words in the sentence with some weight corresponding to the attention. So I can think of that as a graph between the positions in the sentence. And I want to make a very flaky but conceptually useful analogy between this attention graph and a dependency parse. right? So in a dependency parse, you take a head word and you say, what words does this phrase depend upon? And that's a kind of directed graph over the words in the sentence. So from an intuitive point of view, I just want to, and I think this was part of the motivation for the self-attention architecture, that you can think of these attentions as analogous to dependency edges in a graph. Now, in a normal dependency parse of a sentence, the edges have labels. So you might say, well, you've got a verb like said, and it's got a subject and an object. And so the dependency edges from the verb said to the person who said it is labeled as a subject, and the dependency edge to the what was said is labeled as an object. So I'm making a kind of flaky, intuitive analogy, but in the transformer, there are these things called heads. And I want, just to get intuition, I want to make an analogy between the heads and the labels on the edges in a dependency parse. So what's going to happen is that the self-attention constructs a tensor, which I'm going to write as alpha. It's the attention tensor. And it has a head index. That's saying intuitively, what's the label of this edge, of the edges defined by this attention? So this is like an edge label. The attention is directed. It's from T1 to T2. So it's the attention that T1 is paying to T2 under the label K. So that's the intuition. Of course, the actual architecture does not make this intuition explicit, and this intuition is only applicable maybe for some of the time. We don't, as in all neural networks, we build an architecture, we train it, it does something really startling and powerful, and we don't really understand what it's doing. So that's some of the, people have tried to understand the transformers, and there are lots of papers on it, but I just want to point out that it's a difficult problem to understand what it's doing. But formally, we have these heads. And so now I'm going to describe how we build this attention, how the attention is constructed in the transformer architecture. So for each head and position, we're going to compute a key vector and a query vector. So remember, these are layered. So I'm going to use the subscript L to talk about what layer in the network we're in. So little l is telling us what layer we're in. And we're taking an input layer here. So this is a generic self-attention layer. It takes an input. Remember, all these layers are matrices that assign a vector to each position in time. So this is a vector at time t. Capital J means it's a vector. We're thinking of this as a slice into this. And we have a matrix specific to this layer of the transformer, which is simply multiplying this vector. So this is a matrix vector multiplication. And it's going to give us a number for neuron I, a query number for neuron I at position t. So this with a capital I would be a vector, a query vector for the head k at position t. So for each position, we're constructing a query vector at that position by applying a matrix to the vector at that position that's in this layer. And then we also do the same thing. We construct a key. So for each position, we're constructing a query. And for each position, we're constructing a key. And then we're going to construct the attention. And the attention is from T1 to T2. So it's an attention over T2. So what that means in an attention is that if we fix K and T1, we've got a probability distribution over T2. For each K and each T1, there's a probability distribution over T2. And the probability distribution is always constructed with a softmax. So we're going to take so this is going to be a softmax over T2. And let's just, of the query vector, this is the query vector at T1 under this head, and the key vector at T2 under this head. So T1 is putting out a query, T2 is putting out a key, and I look at the match between the query and the key, and I take a softmax over that to get the attention. T1 puts out the query, T2 puts out the key, the softmax determines this directed edge from T1 to T2. Now there's this interesting thing that is done in the transformer architecture. They scale this inner product by 1 over the square root of I. In a softmax, if I put a constant here, that acts as a temperature parameter in the softmax. So that if you are familiar with the Boltzmann distribution in physics, which is basically the softmax equation is converting an energy to a probability via Boltzmann's equation. There's a temperature parameter. So this is taking a temperature parameter to be 1 over the square root of the dimension that's being contracted, right? So this is a sum, this product is a sum over I. And a sum over I has the variance of that sum, if we think of those elements of those as random numbers, if we think the elements of the vectors as random numbers, the variance of that sum goes like the square root of the number of terms we add. And so if we divide by the variance, we're sort of accounting for the dimension of this. So it's going to make this softmax less sensitive to the choice of the dimension of the query and key vector. They don't explain that very well in the paper, I think. It turns out that why are we looking at the variance of this rather than the mean? The mean sort of drops out of the equation. If you add a constant to a vector across all of the, if I were to say to subtract the mean, that's essentially adding a constant across all the elements. If you think about what happens when you add a constant to the energy, when you go from the energy to the probability distribution, that constant drops out. It appears both in the exponent, in the exponential that's in the numerator, and it also appears in z, and it cancels out. So this makes sense. Okay, so that was a bit of a diversion. Remember what we've got is for a given k and for a given t1, we've got a softmax over a probability distribution over t2. Now, how do we compute? So attention computes a probability distribution, and then it uses that probability distribution to compute a convex combination of some values. So what we're going to do is in here is we're also going to compute a value at each position. So we get a value for head k at position t, and that value is going to have it's going to be a vector. If I use the capital I there, that's the vector the value vector we're computing. That value vector is computed the same way that the query vector and the key vector are computed. It's just a matrix it's a matrix specific to the value applied to the vector at this position t. Okay, so we get a query, a key, and a value all computed the same way. And then what we do is we're going to construct a first, I'm just going to do this in pieces. We're going to get a first layer, which is, this is the convex combination. This is taking the attention over t, over the other position, and we're taking a convex combination. When we sum over t, this is a capital T and a capital T here. So we're summing over t, and we're taking a convex combination over this second position, and for each weight in that second position, we're taking the value from that second position and putting it in here. I could have used a capital I here and a capital I here. This is taking this vector, it is taking a convex combination of these value vectors over the positions weighted by this, and that gives us a vector, a value vector at this position for head k. Okay, now we've got many heads. So far I've computed a value vector for each head. Now when we go to the next layer, we've got to get this back into the same shape. So we've got to take all those vectors for the different heads and put them back into the same shape, which is one vector at every position. So we've got to take the different vectors for the different heads and combine them to get one vector at the position. And the first thing we do is just take all the different heads. There are capital K different heads. You take all of the different heads, the head 0, head 1, head K minus 1, and we concatenate them. So we're concatenating all the different heads. So this gives us a value for every head at every position, a vector at every head for every position. This gives us a combined vector at that position that's just the concatenation of all the heads. And then we apply a matrix to this combined thing to get the next layer. So that allows the dimension capital C to be somewhat arbitrary, or capital I. This is capital C is just K times I, right? It's the number of heads times the dimension of each head value vector. And then this can then be reduced to J by applying a matrix that goes from whatever the dimension of C is down to the dimension of J. And this is just a matrix that multiplies this vector. Oh, and I should have pointed out that I'm using this semicolon notation, and I'll use that again to indicate vector concatenation. Okay, now what I just described was self-attention. Self-attention constructs this label-directed graph on a layer and uses that label-directed graph to construct another layer of the same shape as the input layer. The transformer layer, or there's a unit in the transformer called the transformer layer, and the transformer layer consists of 6 sublayers. So the first sublayer is the attention. That's what I just described. How you do, that's the most complicated sublayer. How you go from one layer to a layer of the same shape using this self-attention mechanism. Then there's you take the result of that. This is the result of the self-attention, and you make it part of a residual connection, right? You take the input layer and the thing that comes out of the self-attention and you add them together. And as I said in an earlier unit, residual connections are everywhere now. Again, residual connections are a fairly recent thing that has really, they're everywhere. Then there's a normalization layer. This is analogous to batch normalization, but it's not batch normalization. It's something called layer normalization. And in the second unit on the transformer, I'm going to go through that one. And then there's a feed forward layer that operates at each position, time position independently. It's not looking across time, just each time independently is passed through a feed forward layer. That is included in a residual connection again. So this transformer layer has 2 residual connections. Each of these gets pumped through a residual connection. And finally, there's a normalization layer that produces the output of the transformer layer. And here's a picture. I've stooped to a picture. So we've got some layer coming in here. This box is the transformer layer consisting of what I'm representing as 6 sublayers, because each residual connection, I've made a layer also. So we've got the self-attention, we've got the residual connection that adds and normalizes. We've got a residual connection followed by a normalization layer. We do a feed forward layer that acts at each position independently. Then we make that part of a residual connection, we add and then we normalize. And that's the transformer layer. So if you read a paper and you say our transformer has 15 layers, modern transformers can have 20 layers. When they say a transformer layer, they're talking about this unit of 6 sublayers. And so this picture just shows 2 of them stacked together. Okay, so that's the first unit on transformers. The second unit is really sort of just odds and ends. We're going to talk about what layer normalization is as opposed to batch normalization. And we're going to have some fun examples of what's been done recently with the transformer. So thanks.